Okay, guys, today we're continuing the Newton's laws with the second law, but first we want to remind you of the first law. So last time we talked about how an object at rest will remain at rest, or an object in motion will remain in motion, and when it's in motion, it will stay in a straight line path, so no turning going on, unless acted upon by another force. So another outside force can make the object at rest go into motion, or in motion stop, slow down, speed up, turn left, right, up, down, whatever it might be.
This is an air track. When the pump's running, air comes out of these little holes. And it can support the weight of a scooter, like this one. Now, when I place the scooter on the track and let go of it, it just sits there. It doesn't move unless I give it a push. Then it keeps moving unless I give it another push. Or it hits the end of the track. Or maybe another scooter, another scooter, another scooter. Now here's the thing. If we had enough track and enough air, the scooters would keep scooting forever. There'd be nothing to slow them down.
Well, hardly anything. So when something's at rest or sitting still, it stays sitting still.
Unless acted on by an outside force. And when something's moving, it keeps moving. Unless acted on by an outside force. Outside force. Outside force. This is true of everything that you can touch and see. As you may know,
inertia is a property of matter.
Inertia is a property of matter.
So on the second law, it talks about how quickly objects will accelerate. So basically what it says, if there is a net force acting on an object, the object will accelerate in that direction. And by that direction, we mean the direction the net force is pointing. So if the net force is going to the right, the object will accelerate to the right.
Okay!
There could be forces acting on the object, but the key here is for unbalanced forces to be present. Because if everything's balanced, the net force is zero. So nothing will change in terms of motion for the object. But when we have an unbalanced net force, it means a net force is greater than zero. That's when changes in motion happen. So we have an equation for the second law. It can be written a couple different ways depending on the textbook. You could either solve for force, which in this case, when you solve for force, we're pretty much saying net force. Okay, so when you solve for force, you're actually solving for net force. And that's just, you take the mass, it has to be in kilograms. So we'll make a little note here. Mass has to be in kilograms. And you multiply it by acceleration. Acceleration is meters per second squared. So if all those labels agree, then you'll get the net force. And that's going to be in newtons. And we'll show you how labels work out in a little bit. The other way that you could do this is solving for acceleration. So in this case, force is in newtons or kilograms meters per second squared, and we'll show you that. And mass needs to be in kilograms, and if you do that, you will get your acceleration in meters per second squared. So one of those two things.
Second law. To move a mass, you need a force. Here's a mass.
Hey,
And here's a force.
it's hard to maintain this position, you know. Thank you.
And then in mathematics, we say force equals mass times acceleration. F equals ma.
So in order to get the same mass accelerating twice as much, you need twice as much force.
Here's the mass, and here is twice as much force.
Yeah, for sure.
You could use one of those circle charts in order to solve for these. So since it is just three variables in an equation, we could set up a circle chart for it. But typically, we will only need these two equations. On rare occasions, we might figure out a mass, but these two are going to be the main players for us. So the circle chart would look like this. So for example, if we wanted to solve for force, we just kind of cover that up and we get mass and acceleration right next to each other, which means we're going to multiply.
Oh my God.
If we wanted to solve for acceleration, we have to do the same thing. We just cover up acceleration, force. This right here means divided by mass. So we got our equations there.
Oh my God.
And just to be thorough, if we wanted to solve for mass, which we don't have to, get rid of these little dots here. We don't have to a lot in here, but if we cover up mass, we get force, and that's divided by acceleration.
Oh my God.
So we got three equations on one chart here, and some people like them. Again, you don't have to use them. If you're good at just picking out an equation, you can do that, no problem. Just watch your labels and make sure your label makes sense to what you're trying to solve for. So we'll do an example. So if a 5 kilogram object is accelerating at a rate of 25 meters per second square, what's the force being applied to the object? And by force, we're going to calculate, remember, net force being applied. So there could be like 15 forces on the object, but what we calculate is the net force that's affecting the motion. So we know we're solving for force, so we just need that mass times acceleration equation. So if we're looking at the problem, we see kilograms. That would be our mass. We see 25 meters per second is the big clue, meters per second squared, sorry, is the big clue here. So we know 25 is our acceleration. So we just plug them in where they go. So the math part, the number part of this shouldn't be too bad. We just take 5 times 25 and see what you get.
Do it.
All right, so 5 times 25, we should get 125. But the label part is the tricky part here. So you got to remember back to the first law. What label should this have, since it is a force?
You can do it!
And you should have answered newtons.
What?
And it doesn't make a lot of sense if you just look at it. We got kilograms, meters, seconds, and the seconds is even squared, but we end up with newtons. We'll show you how that works out.
Okay!
Because that should be kilograms times meters per second squared for the label. You can write that as a label. That is no problem whatsoever. However, it was renamed to honor Newton, so it's named newtons. All it did was make your life a little harder that you have to remember more. So newton's easy to remember though. But if you put this for a label, hopefully written a little better than I did, you're not wrong. I mean, you could do that. You could put kilograms times meters per second squared, since nothing cancels out here. You got to keep it all. All right, so our second example, we're going to solve for something different. A 15 kilogram object is experiencing a net force of 30 newtons. What is the rate of acceleration? So we know our acceleration equation if we went back to that circle chart, or we just looked up the equation. Acceleration is force divided by mass. And again, force is what? Net force. And that's spelled out for us right here. Net force is 30. So in our problem, we have 30 is the force because we know that because of newtons right here. And 15 is the mass, and we know that because of kilograms. Kilograms is a mass measurement. So when we plug those in where they go, 30 goes on top, 15 on bottom. The number part of the problem should be pretty easy to deal with, but our label is going to get a little messy here because we have newtons here, kilograms here. So what a lot of people want to do is newtons over kilograms. Technically, if you wanted to leave it like that, you're not totally wrong, but it's very uncommon to have that. So what we want to do is simplify this label to make more sense. So see what you get for the number part of the answer.
Do it. Do it.
Okay, in this case, you should have got 2. 30 divided by 15 shouldn't have been an issue. But for the label part, since we are talking about an acceleration, what should be the label on our number?
You can do it!
Should have got meters per second squared for this one because it is an acceleration. And I did say during acceleration, I'm never going to trick you in this class. If it is an acceleration problem, it has meters per second squared as the acceleration label.
Okay!
Okay, so we'll see in the next slide, you can kind of just follow along with us. We'll see where this comes from that. So how did we get that meters per second squared? So we have to remember saying the Newton is the same thing as saying kilograms times meters per second squared. They're interchangeable. This was renamed to Newton. So if we wrote that and we have our units cancel out, this was the problem. 30 kilograms meters per second squared, but remember in the problem we wrote that as newtons. But now we're not going to change the name of it. We're just going to leave it as kilograms times meters per second squared. Then we divided by mass, 15 kilograms. So if that happens for us, the kilograms on top and bottom cancel out, and we're left with meters per second squared. And that's where our answer comes from. So Newton means the same thing as kilogram meters per second squared. Again, by renaming it, they just made your life a little more difficult. So when we deal with this law will really tell us the difference between gravity and weight. So we're going to need that for later on calculations of weight and acceleration of gravity. So we're going to see how force equals mass times acceleration actually equals our weight equation. And this will tell us the difference between mass and weight. All right, so how do they relate? So this was our second law equation. Force is mass times acceleration. So we're going to rename force here. And all we're going to do is rename it to weight. And when we get our weight, it's going to be in newtons. So we're not going to deal with pounds and anything like that. We're going to deal with weight in newtons because weight is a force. If you don't believe that, have somebody stand on top of you. It is a force. Mass is still mass, however many kilograms it is. And it's important to note that mass has to be measured in kilograms. And the acceleration, that's where gravity comes in. Gravity makes the weight happen. So we're going to rename that G on this. So basically our equation turns to W equals mg. Weight equals mass times gravity. So gravity is a constant number for Earth, and it would be different for different planets or moons or whatever it is. Gravity is going to be 9.8 meters per second squared. For homework purposes, we can usually round to 10 just to make our life a little easier. You show you understand what's going on, you just don't want to make a decimal mistake. But for like lab situations, you have a calculator on your computer, so 9.8 meters per second squared would be the best to use. If the question wants you to use 10 specifically, it usually will say that. So just kind of keep that in mind. So gravity we'll talk about later, but we're going to need this stuff during that talk. So we can see how net forces work out in falling objects motion. That concludes the second law notes, but make sure you finish the video so that it is 100% complete. Then move on to the next thing.